dear students. Glad to meet you again in this session. In this session 2.9, we are going to discuss about shapes of atomic orbital from chapter 2, structure of atom in grade 11. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions. In session 2.1, we have discussed subatomic particles and its classifications. In session 2.2, we have discussed the atomic model, that is J.J. Thomson atomic model, Rutherford atomic model and its drawbacks. In session 2.3, we have discussed the dual nature of electromagnetic radiation. In session 2.4, we have seen the continuous spectrum, emission spectrum, absorption spectrum, atomic spectrum, and line spectrum of hydrogen. In session 2.5, we have discussed the postulates and explanation of Bohr's atomic model for hydrogen atom, line spectrum of hydrogen atom, and limitations of Bohr's model. In session 2.6, we have discussed the two developments, that is de Broglie's relationship and Heisenberg's uncertainty principle that leads towards quantum mechanical model of atom. In session 2.7, we have discussed quantum mechanical model of an atom. In that, we have discussed Schrödinger wave equation, significance of psi, the wave function. In session 2.8, we have discussed orbital and quantum numbers. We have discussed four quantum numbers: principal quantum number, azimuthal quantum number, magnetic quantum number, and electron spin quantum number. Learning outcomes. Students, at the end of this session, you will be able to distinguish radial wave function and angular wave function, interpret the orbital wave function of 1s and 2s orbitals, explain radial probability density and probability density curve of 1s and 2s orbitals, interpret the radial probability distribution function of 1s, 2s, 3s, 3p, and 3d orbitals, and finally elucidate boundary surface diagrams, angular distribution function, and shapes of orbitals. Before getting into today's concept, let us recall Schrödinger wave equation. In quantum mechanics, the behavior of an electron in an atom is described by an equation known as Schrödinger wave equation. In this Schrödinger wave equation, the Greek letter psi is the amplitude of the electron wave called wave function. Solution of the above equation, that is the Schrödinger equation, gives eigenvalues and its corresponding wave function. Orbital wave function. To understand the distribution of electrons around the nucleus, it's very important to know about wave function. An orbital wave function psi is a product of radial function and angular function. The radial function is the function of distance from nucleus. We'll represent it by capital R of small r, and the angular function is the function of two angle variables, that is f of theta and g of phi. So we can write the wave function psi of r comma theta comma phi is equal to capital R of r, that is the radial function, into the angular function. What are all the angular function? F of theta into g of phi. Now let us see what is r, theta, and phi. To solve Schrödinger wave equation in spherical coordinates, consider the location at a point P in the spherical coordinate system relative to the Cartesian coordinates. What are all the Cartesian coordinates? X-axis, Y-axis, and Z-axis. R is the length of the line between the origin, this point O, and the point P. Theta is the angle between the line OP and the Z-axis. And the angle, that projection of this line OP in the XY plane. Here you could see the dotted lines, right? This is the projection of this line OP in the XY plane, makes with X-axis is phi. So R, theta, and phi are the spherical coordinates at point P. As we know that orbital wave function is the product of radial part and angular part. The radial part depends upon the principal quantum number n and the azimuthal quantum number L. So the radial part gives the size of the orbital, but the angular part depends upon the azimuthal quantum number L and the magnetic quantum number M, which gives the orientation of the orbital. So the angular part gives the shape of the orbital. The orbital wave function psi has no physical meaning. If we plot graphs for orbital wave function of different orbitals like 1s, 2s with the difference from the nucleus, they differ from each other. Radial probability density. According to the German scientist Max Born, the square of the wave function psi square at a point gives the probability density of the electron at that point. So the measure of the probability of finding the electron in unit volume around the point P is called the probability density. The variation of the probability density of an electron at the point P versus the distance from the nucleus R for 1s and 2s orbital is given in this graph. The probability density curve for 1s is different from the probability density curve of 2s. X-axis shows us R, that is the distance from the nucleus, and y-axis shows us the probability density of an electron. Here in 1s orbital, the probability density is maximum at the nucleus and it decreases sharply as we move away from the nucleus. In 2s orbital, the probability density sharply decreases at 0 and start increasing and reaches a maxima and again approaches 0 as the value of R increases further. So the region where this probability density function is 0 is called nodes. In general, it has been found that ns orbital has n-1 nodes, that is, the number of nodes increases with increase in the principal quantum number. So here in 2s orbital, we have only one node, and in 3s orbital, we have two nodes. We know that the square of the wave function psi square gives the probability of finding the electron at a particular point at a distance r. This graph shows the maximum value of psi square, that is the probability of finding the electron, is maximum near the nucleus. However, the probability of finding the electron in a given spherical sphere, not at a particular point, probability of finding the electron in a given spherical sphere around the nucleus is important. For that, consider the small difference in the volume dV bounded by two spheres of radius r. The first inner sphere with radius r and the outer sphere with radius r plus dr. We know that the volume of the sphere V is equal to 4 by 3 pi r cube. If we differentiate this volume with respect to small difference in the radius, we get dV by dr equal to 4 by 3 pi 3r square. When we differentiate r cube, it will become 3r square. Now we can cancel this 3 in the numerator and in the denominator. So we can write this expression as dV is equal to 4 pi r square dr. Therefore, the probability of finding the electron in a given spherical sphere around the nucleus is given by the expression psi square dV. We can substitute dV by the expression 4 pi r square dr. Now, we know that psi square is the probability density function. In order to express this in radial probability density function, instead of psi square, we can write it as r of r square into 4 pi square dr. The volume of the total probability of the electron in a radial shell between these two spheres is called radial probability distribution function. A graph of radial probability distribution as a function of distance from the nucleus is called radial probability distribution curve. Radial probability distribution curve of 1s orbital of hydrogen shows the maximum probability occurs at 0.52 angstrom. This is equal to Bohr's radius. So this indicates that the maximum probability of finding the electron around the nucleus is at 0.52 angstrom, which was already predicted by Niels Bohr. There is a probability to find the electron at other distance like 2s orbital, 3s orbital, 3p orbital, and 3d orbital of hydrogen. So the radial probability distribution curve for 2s, 3s, 3p, and 3d orbital of hydrogen is given in this slide. Boundary surface diagram. The probability density of an electron is not uniform in an atom. You could see it is very dense in some region and it is very less in some other region, right? Here in 2s orbital also, you could see it is very dense in this particular region and it becomes very less over here. And again, it becomes very dense in this region and it is very less, but the probability density of the electron does not become zero even at a very large distance from the nucleus. Here also you could see some dots which represents the probability of finding the electron, right? And here in this 2s orbital also you could see the probability of finding the electron represented in dots in this region, right? Therefore, it is not possible to draw a boundary which encloses a region of 100% probability. So, we can draw a boundary surface which encloses a region of 90% probability. Like here, you could see the probability density is not constant beyond this circle, right? But within this boundary, the probability density is somewhat constant in this given boundary surface diagram. The probability of finding the electron is dense over here. Then it is taken to be a good representation of the shape of the orbital, which encloses a region or volume in which the probability of finding the electron is high. Angular distribution function. The variation of the probability of locating the electron on a sphere with a nucleus at its center depends upon the azimuthal number, that is the angular quantum number L of the orbital in which the electron is present. Already we have discussed about the spherical coordinates theta and phi, right? It is found that for 1s orbital, the azimuthal quantum number L is equal to 0 and m equal to 0. F of theta is equal to 1 by root 2 and g of phi is equal to 1 by root 2 pi. If we multiply these two spherical coordinates, the angular distribution function is given by the expression 1 by 2 root pi. That is, in this expression, there is no theta or phi, right? So it is independent of the angle theta and phi. Since it is independent of theta and phi, it indicates that the probability of finding the electron at a given distance is equal in all directions. So the boundary surface diagram for s orbital is actually a sphere centered on the nucleus. The size of s orbital increases with increase in the principal quantum number n. That is, the size of the 4s orbital is greater than the size of 3s, which is greater than the size of 2s, which is greater than the size of 1s. Now let us see the shape of the 2p orbital. The p orbital consists of two sections called lobes that passes through the center of the nucleus. We know that the region where the probability density function reduces to 0 is called the nodal surface or nodal plane or angular node. The probability density function is 0 on this plane. The size, shape, and energy of three orbitals are identical, but they differ only in the orientation. The axes of these three p orbitals are mutually perpendicular to each other. Like s orbitals, p orbitals also increase in size and energy with increase in the principal quantum number n. That is, the size of 4p orbital is greater than the size of 3p orbital, which is greater than the size of 2p orbital. Students, you need to note that no such nodal planes or angular planes you could find in s orbital. That is why all the s orbitals are spherical in shape, and that is the probability of finding the electron is equal in all directions. It is independent of the angular node theta and phi. Angular nodes and radial nodes. Since there is no angular node in s orbital except s orbital, the total number of nodes is the sum of the radial nodes and angular nodes. The angular nodes in an orbital is equal to the azimuthal quantum number L. The number of radial nodes is given by the expression n minus L minus 1, where n is the principal quantum number and L is the azimuthal quantum number. The total number of nodes in an orbital is the sum of angular nodes and radial nodes, right? So it will be equal to L plus n minus L minus 1, which gives the expression n minus 1. So the total number of nodes in an orbital is equal to n minus 1. Let us understand this concept with an example. Let us take 3p orbital. 3 means we know that the principal quantum number n equal to 3 and p represents the azimuthal quantum number L equal to 1, right? We know that p orbitals are dumbbell shaped. If we take the cross section of 3p orbital in this region and at this radius, we get a spherical surface where the probability of finding the electron is 0, right? And this region is called the radial node. There is a plane which passes through the nucleus where the electron is found to be 0. And this plane is called the angular node. So this 3p orbital has one radial node and one angular node. Let us discuss this concept by applying the formula also. Number of angular nodes, that is the azimuthal quantum number for 3p is equal to L equal to 1. And number of radial nodes equal to n minus L minus 1. That is 3 minus 1 minus 1, right? So the total number of nodes in an orbital is equal to the sum of the angular node L and the radial node n minus L minus 1. Substituting the values, we get the total number of nodes in an orbital equal to 2. That is, it has one radial node and one angular node. Shapes of d orbitals. For d orbitals, what is the value of azimuthal quantum number L equal to 2? And what is the value of m? M ranges from -2 to +2, that is -2, -1 through 0, +1 and +2. So it will have 5 values. Since it has 5 values, it has 5 d orbitals. The 5 d orbitals are designated as dxy, dyz, dzz, dx square minus y square, and dz square. If you look at this picture, the first 4 d orbitals have clover leaf shape, but the fifth one differs from others. The 3d orbitals have 2 nodal planes. In this picture, even though it looks like one nodal plane, we have 2 nodal planes because this nodal plane is facing you. Shapes of f orbitals. For f orbital, what is the azimuthal quantum number value L? L equal to 3. And what are all the values of m? M ranges from -3 to +3. That is -3, -2, -1 through 0. It will proceed. Then +1, +2 and +3. So it will have how many values? 7 values. So the 7 f orbitals are designated as fz cube, fxz square, fyz square, fxyz, fx into x square minus 3y square, then fy into 3x square minus y square, and finally fz into x square minus y square. If you look at the pictures of f orbitals, you could see 3 nodal planes along the x-axis, y-axis, and z-axis in these pictures. So, f orbitals have how many nodal planes? 3 nodal planes. Students, let's recall all the topics that we have discussed in this session. We have discussed radial wave function and angular wave function. and we have discussed variation of the orbital wave function of 1s and 2s orbital with distance from nucleus, and radial probability density and the probability density curve of 1s and 2s orbitals. We have discussed radial probability distribution function of 1s, 2s, 3s, 3p and 3d orbitals, and finally we have discussed boundary surface diagram, angular distribution function and shapes of s, p, d and f orbitals. Hope this session was very useful to you. See you soon in the next session. Have a nice day. Thank you.